Okay, let's move on. And for this next chapter, we're going to move away from optimization as a decision analysis tool and look at something a little bit different. We're going to look at decision trees. So we are in the other book now, the Powell book, and it is chapter 13. Although it may be a different chapter because you have a condensed version of the book. Okay, so we want to introduce uncertainty into the mix here, okay? Because some of the problems contain uncertain elements that we're going to face, okay? And so thus far, we have looked at, or the parameters in our problems have been fixed. The data has been fixed, okay? The only thing that's uncertain up to this point has been what our decisions would be to find our optimal solution, okay? But in some cases, it's actually the data inputs, the parameters that are uncertain. Okay, so uncertain parameters are parameters, as we've said, that are subject to uncertainty. We don't know what they will be exactly. Okay, and in fact, we won't know what those parameters, what value those parameters will take until we have made a decision and move forward. Okay, it's like looking at deciding which box to pick up and seeing what's underneath the box. Until you've made the decision, you're never going to know what's inside the box. Okay, and so if a parameter is uncertain, it means it can take on two or more values. Okay, depending upon influences beyond our control. All right, that's what makes them uncertain. They're not decisions that we make. Okay, decisions are in our control. Okay, these are beyond our control. So we call these states of nature or simply states. Okay, and so what we do is we list the possible states if we can, and then for each of those states, the corresponding value of the parameter. So, and then finally, if we can, we assign probabilities to each of the states, so so that the parameter forms a probability distribution. Okay, and we'll get into an example of that in a moment. So let's take a look at something we call a payoff table. All right. For each action and state combination, okay, there's an entry in the table. And usually it's a measure, some kind of economic measure. All right. It's usually in monetary terms, but it doesn't have to be. Okay. And it says that there could be costs or revenues from other applications. So we call this not necessarily profit or revenue. We just call it payoff. Okay. And the example here is a toy company is trying to decide whether to bring out, so say they want to bring out a new toy. And the question is, do they bring out a single version, two versions, or a full line of this toy? All right. And the market can respond either good or fair or poorly. And they have estimated the payoff if for each action state. Okay, so if they bring out a single version and the market response is good, then the payoff is 100. That could be 100,000, 100 million, it doesn't really matter. Okay, and so if you bring out two versions and the market response is good, the payoff would be 200, and then so on. Okay, so this is a very simple payoff table. Okay, so let's take a look at some benchmark criteria for making these decisions. The first one is known as the maximax payoff criterion. All right, we want the largest of the maximum payoffs among our actions. So, looking at our example, the toy example, okay, basically maximax means absolutely the most optimistic So optimistic means that we're going to assume that the market will be good. And if the market is good, we obviously want to choose the full line because that gives us our maximum payoff. All right. However, not everybody is optimistic, and it's not always wise to be absolutely optimistic in business. And so we could use the maxi-min payoff criteria. All right. This seeks the largest of the minimum payoffs among the actions. So the minimum payoffs is pessimistic. So it assumes that our state, the market, will be poor. All right. And if we assume a poor market, then the maximum of the minimum payoffs is rolling out the single version. Okay. Now, just to this looks like the two extremes. Okay, but there is another criteria, and that is called the minimax regret criterion. It seeks the smallest of the maximum regrets among the actions. Now, what does that mean? Well, if, for example, the market is good, all right, and you choose the full line, well, then you have no regrets whatsoever, right? Because you got the maximum payoff. But suppose you chose two versions rather than the full line. You made 200, but you could have made 300. So therefore, your regret is 100. Down to the single version, your regret would be 200. Is the difference between the maximum and what you chose. Okay? And so then we tally up the maximum regrets from those three columns, and we have on the right-hand side our maximum regret. Okay? And so what we want to do is we want the smallest regret possible. Okay? And that means that we choose the full line. Okay? So that if things go better than we hope, we have the least amount of regret. Okay? Sounds crazy, but it works. Now, the problem with the previous examples is it basically just takes a guess at the states, all right, in this case the market, and ignores the other. So you choose one column basically and you ignore the others. Okay? But if we incorporate probabilities, then we can use all of the data. Okay? For example, suppose we decide through analysis, market analysis, or whatever, that the probability of a good market is 20%, of a fair market is 50%, and of a poor market is 30%. All right. So now what we can do is we can use a weighted average of these probabilities times the expected payoff. Okay, so 100 times 0.2 plus 60 times 0.5 plus minus 10 times 0.3 gives you an expected payoff of 47. All right. For two versions, the expected payoff is 53, and for the full line, the expected payoff is 50. So in this particular case, we're going to want to choose two versions. All right. Now we justify this by assuming that we will make a decision like this multiple times. Okay, that's how the probability comes into play. Okay, and so in this particular, this is better than the previous versions of the payoff table because the probabilities allow us to use all of the data rather than picking one and ignoring the rest. So the problem with payoff tables is that if they get much bigger, they can get a little unwieldy and confusing. Okay, so we can take that same information and model it using a probability tree. Okay, and a probability tree is a graphical representation, basically, of the payoff table. All right. The node, there is a node in a probability tree which branches out. Okay, it's called the chance node. All right, and each branch out of that chance node represents a state. Okay, and so, for example, our states would be good, fair, and poor. All right. So each state is a possible resolution of uncertainty represented by the chance node. Okay. And so what we'll do, just like we did in the previous example, is we'll specify probabilities for each of the states, and we'll use those to create distributions to describe uncertainty at the chance node. And again, just kind of bear with me. This is a little bit confusing, but when you see it graphically, it's going to start to make sense. So, for example, here is a simple probability tree. Okay, this is the chance node right here. Okay, this represents our uncertainty. Coming out of the chance node are the states. All right, high, medium, low in this particular case. All right, this is what we do is we can create trees in a series, or portions of the tree in a series. So, for example, coming out of the chance node is the medium probability, okay, and into that we have a series of competitors, 1 through 5, okay. So we could have, again, these represent uncertainty. We could have one competitor, two competitors, three competitors, and so on. And if we have three competitors, our chances of being successful is good, fair, and poor. All right. Now, keep in mind that this is an abbreviated version of this tree. If we were to draw it all out, then at the end of three competitors is good, fair, and poor. And we would need good, fair, and poor at two competitors. We would need good, fair, and poor at one competitors, and so on. And we would also need all of these competitors at each of these other nodes, at the end of these other nodes. Okay? So a decision tree can actually grow quite large very quickly. All right? And so this just gives you an idea. This is still not a very complex decision tree, but as you can see, it can, as you add more uncertainty and more decisions, then it can get ugly in a hurry. Okay, so let's talk about decision trees. Decision trees are basically a formal type of probability tree. Okay, and so there is software that allows us to create decision trees within Excel. All right. And these can represent the elements of our model for making decisions under uncertainty. Okay. And we're people are very visual. Okay. We could do all of this within a payoff table. All right. But this makes can make more sense to us to see it visually. Okay. And it allows us to distinguish between the things that we can control, which are our decisions, and random events, which is the uncertain parameters. Okay? And so in a decision tree, we have choices. Now, these can be the choices of a single decision maker or decision making group, like a committee. Okay? But one way or another, it's a single decision-making agent, whether it's a person or a group. Now, how do we represent decisions in a decision tree? We've already said that a chance node is a circle. Okay, we saw that in the probability tree. Decisions are square nodes. Okay, and so for each decision, there are alternative choices coming out from the decision node. Okay, and so these are the things that are potential actions or courses of action that are available to the decision maker. Okay. Also, for each uncertain event, the alternative states are represented. Okay, and we've seen that already. All right. So let's take a look at the analysis of a decision tree. Okay, we build the tree from left to right. Okay, because that is the time sequence in which a decision is followed. Okay, but we evaluate the tree from right to left. Okay, at each chance node, we can calculate the expected payoff, just like we did in the payoff table. Okay, and we do that by using the probabilities. All right. And then we come up with values based on those probabilities. All right. And the payoff from each of those decisions. And again, relate this back to the example, the payoff table example that we've already done, and you'll see it becomes quite easy. All right. And so we want the largest expected payoff to determine the best action. All right. And we call this rolling back the tree, making the calculations, figuring out our best expected payoff. So here's our decision tree it's the decision tree version of the payoff table that we've been looking at. Okay. So over here on our left is a square box. This represents a decision node. Our decisions are, do we do a single version, two versions, or a full line? The circles represent chance nodes. Okay. Good, fair, and poor markets. Good, fair, and poor. Good, fair, and poor. And then finally the payoffs. Okay. At the end of the tree. The triangle represents the end of the tree. Okay. So we have 100 payoff, but the probability is only 0.2. So 100 times 0.2 plus 60 times 0.5 plus minus 10 times 0.3 gives us an expected payoff of 47. Down here it's 53. Down here it's 50. So obviously we want to choose 53. We want to choose two versions. So we come back here and this is our expected payoff. Okay. We've just rolled back the tree. Okay. So the distribution that we associate with a particular action, it's called its risk profile. So as you saw, we assigned probabilities to each of the states. Okay, those are the risk profile. All right. And so we have the possible economic outcomes, the possible payoff, and the probability of that payoff. Okay, and so what this means is since the inputs are uncertain and we describe them in terms of their probability, then that means that our outputs are also uncertain, and we describe those also in terms of their probability. Okay, and so again, we've moved from the realm of these are our solid inputs and these are our outputs based on our decision to these are probably what our inputs are going to look like. Therefore, this is probably what our output will look like based on certain decisions. Now, decision trees they can be sequential. Okay, sometimes we have multiple sources of uncertainty and multiple sets of decisions to make. So if we were introducing a new product, for example, all right, the first decision would be which channel to use during test marketing. Okay, and then moving on from there, all right, we make a commitment to the marketing channel and we develop estimates of demand based on our market testing. Okay, and then when we go from the test period, we might have to reconsider our channel choice. All right, so this can be an iterative process. All right, you can go back, provide feedback, and make a different decision. Okay, and then when we get to full scale introduction, all right, The profit that we achieve from that depends on the decisions that we made previous, okay, including the channel that we initially chose. So let's take a look at an example here. Okay, we have our telegraphic decision tree in the next slide. Okay, and we choose our initial channel. We observe the test market. We reconsider our choice of a channel, and then finally look at the demand during our full-scale production or full-scale introduction. All right, so our initial, as you can see, our initial market decision is a decision, okay? And then we have three levels of demand, which is a chance coming out of a chance node, okay? Then we decide finally on a marketing channel, okay? And then again, based on that decision, we have a series of chances, which represents our full-scale demand. Okay, and again, we have not drawn out all of these possibilities. This decision tree is actually much bigger than what we're showing you here, but it's just to show you that we can make a decision, have a probabilistic outcome, make another decision, have another probabilistic outcome. These chance nodes are probabilistic branches, okay? And so we can make a series of decisions based on uncertain inputs, okay? And although that sounds risky, okay, it's really basically how we live our lives, all right? Uncertainty is a fact of life. We very seldom have all of the data that we would like to have. And so this is just represents reality. Okay, so let's take a look at some principles for building and analyzing our decision trees. First off, we have to decide what are our essential decisions and the uncertainties. Okay, if you try and factor in every single chance, every single decision, all right, every possible permutation, the decision tree will be way too large. Okay, then we have to decide in what sequence they go. Okay, this is a temporal process. All right, one thing follows another. Okay, so we start the tree with the decision node, okay, representing the first decision. Okay, and we put in a representative number of possible choices for the decision. It does not have to be exhaustive, okay? And you've seen that in the trees that we've displayed. We don't put every single decision in there, otherwise the tree becomes huge, okay? And then for each choice that we make, each decision, we have a chance node representing the uncertain events that follow the decision. All right? We saw that at the very last tree. Decision, chance, decision, chance. And then again we select representative state, or a number of them, for the chance node. And then we continue to expand the tree with decision and chance nodes until the overall outcome can be evaluated. Okay? So again, if you take a look at the previous slide, you'll see that not every decision is listed and not every uncertain outcome is listed. All right? This is simply a way of graphically representing the decision tree, but not with every single not every single chance or decision listed. Now, how do we do the rollback? Okay, again, we do the building from left to right. We roll back, or we analyze the tree from right to left. Okay, so we start with the last set of nodes. These are the ends of the tree. Okay, and then we start calculating the expected payoff. All right, using the weighted average of the probabilities times the economic outputs. All right, and then we replace each chance node by the expected value. All right, and then for each decision we find the best expected value by maximum benefit or minimum cost, and then we continue to work backward. Replace the decision node by the best value, okay, with the node of which choice is best, and we continue to go backwards in this way, just like the toy example. All right, and then in the end we have our decision, okay, and we also have the risk profile that represents that decision. Okay, so let's talk about the cost of uncertainty. As we've said, we've got to take action. The first node in our decision tree is an action node. Okay, so we have to make a decision before we learn how the chance nodes will play out. We have to make a decision before we find out what happens at the uncertainty levels. Okay, and so obviously the situation would be a lot better if we could learn about the uncertain event first and then choose an action. So go back to our toy example. We don't know if the market will be good, fair, or poor, but if we did, we'd be able to make a much more informed decision. So obviously, if we were to know which way the market was going to go, then we would choose the best value in each of those markets. And so that means that we would, if the market was good, we would get 300. If it was fair, we would get 60, and if it was poor, we would get minus 10. Now, if you multiply those maximum values by the probability, you get $87,000. These values are in thousands. Now, the way we did it before, when we didn't know which state the market would take, it was 53. So the difference between those is $34,000. That is the value of uncertainty. Okay, because when we performed our calculations, we decided that the best that we could do under uncertain conditions was 53,000. If we knew which way the market was going to go, factoring in our probabilities, it's 87,000. So that $34,000 represents the value of uncertainty. Imperfect versus perfect information. Okay, as we said, we make the decision before the uncertainty is resolved. Okay, and so we have imperfect information. If it was otherwise, if we could swap those chance nodes and decision nodes around, we would have perfect information. Okay, but we would have a higher payoff. Okay, as we saw on the last slide. Okay, so let's talk about the expected value of perfect information. The $87,000 was what we call the EPPI, the expected payoff with perfect information. All right, it's always going to be as good as the expected payoff from following our original process. Okay, but it will usually be better. And so the expected value of perfect information, or EVPI, is that difference. It's that $34,000. Okay, it's what we would hope to gain with perfect information. Okay, and we can actually model this in the tree structure. Okay, where we reverse the sequence of the decision and the chance events and do the calculations again. So this is what it looks like in the decision tree for the expected value of perfect information. Okay, notice that we have reversed
the decision and the chance nodes. Okay, we have the chance node coming first. So if we start at the right hand side and work backwards, okay, obviously with each decision, all right, we're going to choose the highest payoff, right? Why would we not? All right, and so we're going to choose 300. If the market is good, we are going to choose a single version, 60 if the market is fair, and we're going to choose single version, which is -10 if the market is poor. Okay, and so we have that -10 value, the 60 value, and the 300 value, and we multiply it by the probabilities. 300 times 0.2 plus 60 times 0.5 and -10 times 0.3, and we get our value, our expected payoff of perfect information, all right, is 87. All right, and we subtract that from our original value, or we subtract our original value from it, and we get 34, our expected value of perfect information. It's a little bit confusing. EVPI, EVPI, EPPI. Okay, EPPI is the payoff, and EVPI is the difference between the perfect payoff and our original calculation. Drawing a decision tree out manually and doing the analysis by hand, although it can be done as we've shown, is time consuming, and it can get a little sloppy, and it's not the kind of thing that you would do to present to stakeholders or decision makers. So we want to have some kind of tool to do this in a much more professional way. All right, so we're going to use decision tree software, which is contained in the Analytics Solver platform, which hopefully by now you have downloaded and installed, and it is an add-on for the Excel program. Okay, now the next several slides in the original PowerPoint are about using the decision tree software, but I don't find that that's particularly helpful. I'm going to hide those slides. I'm going to leave them in the slideshow. I'm going to hide them and just get to the more important things, and I will demonstrate the use of the decision tree software when we meet during our online sessions. I will show you that this is the what the full diagram looks like from our toy example, in using the decision tree software in Analytics Solver. Now, when you create a decision tree, you're actually creating a spreadsheet. Okay, and so it has the properties of a spreadsheet, and so you can manipulate and do analysis just like you would with a spreadsheet. Okay, so we can perform like a sensitivity analysis, for example, using TreePlan. Okay, so here is an example of a sensitivity analysis using our example model. Okay, we can change the parameters and run the sensitivity analysis and see how the values change, and I will demonstrate this when we meet in our online session. So far we've been assessing our decision tree by monetary payoff, okay, and that makes sense. But what if we wanted to incorporate some kind of a risk portion in whatever measurement we were using to assess our decision tree? After all, we are talking about uncertainty. Okay, so if we could just take that monetary value and adjust it for risk, we might have a better idea of the decisions that we need to make. Okay, well, we can do that, and we'll do it by adjusting our monetary value for risk using a function, and the result will be what we call utils, all right, or utility. All right, so we will be maximizing now, not for monetary payoff, but for maximum expected utility using the utils unit. Okay, and our decision tree software allows us to do that. Okay. Now, the theory behind the function is a little more than we'll get into in this class, but trust me, it is a standard utility function. Okay, and so the utility function that we're going to use is the exponential utility function. Okay, and you can see it there on your screen. D is the value of the outcome in dollars. U is the utility value. That's the value that we're going to use now. All right, A and B and R are parameters of the utility function. Okay, and typically A and B will be set to 1. All right, and R is the parameter that influences the shape of the curve. It's typically convex. All right, and it's known as the risk tolerance. Okay, so we'll do this in decision tree. Okay, but the decision tree software will use the function to convert the monetary outcomes from dollars to utils. All right, incorporating the risk of an unpleasant outcome. All right, and as I said, we usually set A and B to 1. Okay, and what that allows us to do, really, just in practical terms, is the function will pass through the origin. Okay, so then really all we have to do is find the value of R. Okay, and this is a typical graph of the utility function. All right, on the x-axis is monetary payoff, and on the y-axis or the vertical axis is the utils. Okay, and as you can see, there is a point of quickly diminishing returns in terms of utility. All right, so that is very different than what we were looking for in terms of monetary payoff. So when you incorporate risk into the function, it gives you a little different result. Okay, so in decision tree, what we'll do, and I'll show you how to do this, is specify the 3 parameters. Okay, and I'm not going to go through the task pane and all that. I will show you that. Okay. Now, kind of an abrupt ending here, but those are the things that I'm going to show you. There's a lot of demonstration to be done in our online session, but basically what we've done in this chapter is to incorporate in uncertainty, okay, which is really a practical thing to do because a lot of the times the data that you have is uncertain. Okay, you might know a range, you might know a probability, but you don't necessarily know the input parameters exactly. And so we can use things like payoff tables and decision trees to incorporate uncertainty into our decision making process. And while we can do those things manually, there's a software program, there's actually many that allow us to automate the process. Okay, and not only can we incorporate risk into the process, but ultimately determine monetary value, we can also create an outcome in a measurement called utils that incorporates money and risk into a single measurement, and that can be handy. And that's it. We will get to this, a lot of the demonstration, in our online session. And until then, we'll see you later.